So now we've defined connectivity and connected components, and this is basically a way of measuring how connected a graph is, but it's a very blunt, sort of basic way of saying either the graph is in one piece or it is in many pieces. So now let's talk about vertex and edge connectivity, which are basically slightly more refined versions of saying how highly connected a graph is. So let me write that down. More refined idea of how highly connected a graph is. And basically, the way we'll define these things is how many vertices or edges do you need to remove in order to disconnect the graph. So let's go through this in detail. If removing a vertex from a graph disconnects the graph, we call that vertex a cut vertex. Basically because if we can, we can cut the graph in two by cutting at that vertex, essentially. And similarly, if removing an edge disconnects the graph, call it a cut edge. Same reason. We can cut the graph in half by cutting at that edge. So for example, let's consider this graph. And first of all, just intuitively, we can see that this is connected, but maybe you want to be more refined and say that this is only kind of tenuously connected. It has a lot of vertices, and it has not a lot of edges connecting them. It could be a lot more connected than it is. So cut vertices and cut edges are one way of talking about this precisely. So in this graph, for example, we can see that if we cut this vertex off of the graph, it remains connected. So that is not a cut vertex. On the other hand, if we remove this vertex from the graph, now our graph is disconnected. So that is a cut vertex. And this one as well, let's just do that real fast. If you cut this off, it disconnects the graph as well. So these are cut vertices. So in this graph, we have exactly 2 cut vertices, and the other 4 are not cut vertices. What about our edges? If we remove this edge, for example, our graph remains connected, no problem there. So this is not a cut edge. In fact, the only one is this middle edge. We cut that guy, now we have a disconnected graph. So we have one cut edge in this graph, it is the middle guy here. And let's consider another example. This graph is more compact, more held together, and you can quantify that in the fact that it has no cut vertices and no cut edges. Just to do some examples, If we remove this vertex, it's still connected. If we remove this vertex, it's still connected. And for example, if we remove any of these edges, it is going to be still connected. So there's no single vertex and no single edge that we can remove to disconnect this graph. And that's a way of saying that this graph is more highly connected than this one. So let's quantify this even further. If G is a graph with some vertices and some edges, a subset of the set of vertices is called a vertex cut. If removing all vertices in the subset disconnects the graph. Removing all vertices in V prime disconnects G. And similarly, a subset of the edges is an edge cut. If removing those edges in E prime disconnects the graph. So this is more refined even than asking if there's a cut vertex or a cut edge. It's asking, can you cut a bigger number of vertices or a bigger number of edges to disconnect the graph? And we can use this to define more, more refined versions of connectivity, namely the vertex connectivity of G is denoted kappa of G. So this is the lowercase Greek letter kappa, or at least that's how I write it. The vertex connectivity is denoted kappa of G, and it is equal to the number of vertices in the smallest possible vertex cut. So what is the minimum number of vertices that you need to cut in order to disconnect the graph? That is the vertex connectivity. And similarly, the edge connectivity is denoted lambda of G. So this is lowercase Greek letter lambda. And it is equal to the number of edges in the smallest possible edge cut. So let's do some examples. So let's start with this graph, and let's compute its. So we observed before that this graph has no cut edges and no cut vertices. So no cut vertices. So we can interpret that as saying that the vertex connectivity, kappa of G, is greater than 1. You cannot cut it with one vertex, so the smallest possible vertex cut is going to take more than one vertex. And note that if we remove these two vertices, we get this disconnected graph. So A and B form a vertex cut. So in fact, the vertex connectivity is exactly 2, because we can't do it with one vertex, but we can do it with two vertices. And we make an exception. So for vertex connectivity, we need to treat complete graphs differently, because a complete graph has no vertex cuts. So let's just verify that in an example real fast. Let's just use the complete graph on 3 vertices, namely a triangle. And let's just check them all. If we remove this vertex, it's still connected. And similarly, this vertex or this vertex, all still connected. If we remove both of these, it's still connected. And similarly, both of these or both of these, still connected. So there's no way to disconnect a complete graph by only cutting vertices. Basically because removing any vertices results in another complete graph with fewer vertices. So for example, when we delete this vertex from this graph, you can see that it becomes the complete graph on 2 vertices instead of the complete graph on 3. And that'll always happen. If you take the complete graph on n vertices and you remove vertex, you get the complete graph on n minus 1 vertices. And that's never going to be disconnected. So we make this exception, and we define kappa of the complete graph on n vertices, which remember we denote by kn. We just define this to be n minus 1. And this is a reasonable thing to do, because for non-complete graphs, which is to say all other graphs, the vertex connectivity is going to be between 0 and n minus 2. So it's going to be 0 if it's disconnected, and it's going to be n minus 2, for example, if it's a complete graph minus a single edge. But maybe that's a good exercise to verify that if you are curious. So we have this small exception for vertex connectivity. There's no exceptions needed for edge connectivity. We can treat complete graphs exactly the same way. Although it's still true, so let me write that. No exception for edge connectivity. But still true that the edge connectivity is equal to n minus 1 if and only if G is a complete graph, which is a good exercise as well to verify this. So let's see some examples of edge connectivity. So let's take our good old example. We saw that this has no cut edges. So the edge connectivity is greater than 1. And let's see, can we cut it with 2 edges? So one way of seeing this is that we have a vertex of degree 2. And so if we cut both the edges connecting to that vertex, we will disconnect the graph because we will leave that vertex floating in space. So edge connectivity has this, this nice relationship to vertex degree, which you can work out if you're interested, and will probably be helpful for the homework. So it has a vertex of degree 2. So, oh, my pen. Those 2 edges form an edge cut. So because we can't do it with 1 edge, and we can do it with 2 edges, we see that the edge connectivity is exactly 2. Very good. And I will leave it to you as an exercise to find out the precise relationship between edge connectivity and degrees of vertices. But I do want to give another example to show that it's not just that it's the degree of the lowest, the lowest degree of a vertex. So for example, if we have a graph like this, all vertices have degree at least 3, which you can just check by looking at it. I think these ones have degree 3, and these ones have degree 4. But you can also see that if you cut these 2 edges right down the center, you will see that the edge connectivity is 2. So now we have paths and connectivity, and we also have vertex and edge connectivity to give us a more refined idea of how highly connected a graph is.